Welcome to another Syvecs help video. This help video is based on the wastegate control of the S7, S8 and S12 range of ECUs. Some people that have now actually upgraded to an S7 have asked for more information about the wastegate strategies that are used in the newer ECUs compared to the S6. The S6 was a lot more simplified, and now that the S7 has a lot more advanced functions, some parts are different, and we want to go over today the differences between those two ECU strategies. So the first thing obviously to make sure of with any wastegate control strategy is that you have a manifold pressure sensor that's reading and assigned as seen here, and also that we have a wastegate control solenoid assigned as well. The anti-phase control allows you to use another solenoid for the top or bottom hat control of the wastegate, so you can have independent control of both parts of the wastegate if wanted. This is covered more in the earlier wastegate control on the S6. The ability to have two wastegate outputs also is useful if you are running a split bank control, i.e. you have two map sensors and each map sensor is corresponding to one bank of the engine. And then what you can do is you can use the second wastegate control solenoid, which will follow and control based on the second manifold pressure value. If you are using that function of doing it that way, just make sure under engine controls fundamentals, your bank allocation is set up correctly so that the corresponding cylinder matches the bank allocation set. Okay, let's head to the wastegate control and go over this a bit more. Now the differences are now that you actually can see that the control valves is in a separate section. So you've got the ability to control the wastegate control output based on either a low side, half bridge or full bridge. The full bridge option is there for people that are wanting to use full motor control wastegate solenoids, and there are those coming available now more in the market. So if you've got a motor that actually controls the wastegate position compared to an actual pneumatic air pressure, you would use the full bridge for controlling the motor. Another way you can actually do that is via the supercharger bypass strategy and using the closed loop boost control there. Now the PWM frequency is obvious, and the battery adder allows you to adjust the opening time of the millisecond time of the solenoid based on your battery voltage. Generally those are just set as 0 because most applications will be running at a set 14 volts. If you do know the offset curve for your solenoid based on voltage, then you can populate that in there if you wish. But for most applications, it will just be that the output drive type is set as low side. Once that's done, we then need to scroll down to the standard strategy part and go over the areas in here. So you've got your engine speed breakpoints, which is self-explanatory, and then you've got the enable point. So this is the point above this threshold that the strategy would come enabled. So this is currently active just from 0% throttle. You can normally have recommended that to be something like 30%. So the solenoid's not always clicking away. And then you've got an enable speed and an enable barometric pressure offset. Heading to the map control, this is the area where it's slightly different compared to the S6. So I'm just going to go over all of these calibrations to understand them. Now I won't go over every single calibration that's in the wastegate control. I'm just going to go over the ones that are important for users that want to actually just control generic wastegate control for a turbocharged engine and not in like a rally application, etc., stuff like that. So the minimum manifold pressure target, this is the lowest manifold pressure target that you can allow. So on this particular car, I've got it set at 1900, so that's 0.9 bar. And then the calibration switch map target adder effect. Now this is important to look at because the adjustments that you make under calibration switches will affect either your maximum target or your target limit. Now the differences between those, these are the manifold pressure maximum targets, and this is on the S6 what you'd normally be using to populate your targets in. With the S7, S12 and S8 later firmware, you have the stage target limit, and this is generally your maximum kind of limit that would be set in here, and then you can actually have adjustments here based on the stability of that, which I'll come back to a bit later. So the calibration switch map adder target, under calibration switch here, wastegate control, where you set your obviously strategy maximum target map is obviously here. So this corresponds to these targets here. And then the manifold pressure target adjustment. Now this is what this calibration is for here. Does it affect the target limit or the maximum target. So when you adjust, if you have got calibration switches and you're wanting to lower the boost per calibration switch, when you adjust that, what that actually is changing is the stage target. So we can actually open that and plot that. So if we go to here and actually look at your wastegate map max and wastegate target and wastegate map limit, you can see here that now if I come into got the map center to 1, calibration select here. If I set this back to 0, you'll see that the wastegate map limit is the one that's being adjusted, not the map target. Okay. Now if I then go back to this setting here and change this to maximum target, you can then see it adjusts the actual maximum targets that are set here. So under your map control, just close this, your maximum target. Now you've got 2000 in there. When you adjust the target adjustment here, it now affects that maximum target. Coming back to the standard strategy control, I would suggest probably the best way to do that is based on the maximum target. It saves you having to use the stage target limit then, which has a lot more functionality, and that way it matches what is used on the S6. If you did want to use the stage target limit, this is generally used in a rally application in the staged area, and you can actually set here stable error thresholds and stable times. This is because a lot of the time it will be heavily on anti-lag, on launch control, etc., and the stability of the manifold pressure will be a lot less stable than if you were just say on load during a turbocharged engine on boost, etc. So coming back to this, if you at the moment you can see the CM maps are adjusting the wastegate map limit, and I'll come back to how you can adjust those later. So the maximum manifold pressure target maps are pretty self-explanatory. If you are using flex fuel, remember that it will blend between these two tables in doing so. So just to make that aware. And then coming down to here, you've got a target multiplier based on air charge temp. You've got a progression demand select, so that would be based on either the drive-by-wire target, pedal, or TPS. And this is your target progression table. So if you were at 50% throttle, the actual target would be adjusted to 0.66% as a multiplier. Think of it that way as a percentage. So what I mean by that, at the moment it's 100%. If I put that to 50, you can see that the adjustments are characterized on that. Now you've got your error breakpoints and derivative breakpoints. This is your closed loop kind of on the S6, the closed loop adjustment table. This table is the inverse of how it's done on the S6, so that's an important point. The reason for that is the manifold error control is always set into a percentage, and it's easier for the calculations to work as a percentage based when it's inverted. So basically the way this would work is if we bring up, let's just open some gauges now that are important. So if we open up manifold pressure and our target, limit, wastegate target, and wastegate limit, and max again. And then we're going to look at our error, which is important. So our wastegate manifold pressure error. Just open this so it's a larger size. You can obviously put these into different gauges if you want. You can put them into a trace to do it like that, so you can view it, and you can even put these into one big gauge if wanted, which is covered in another video. So if you look for on YouTube the Syvecs gauges setup, it will explain how you can make this all into one gauge with all the variables so they can overlay each other. So at the moment we can see that our manifold pressure here is actually 1895 millibar, and our target is actually 2000. So we're actually, the error that's created is minus 105. And then what you can do in here is this obviously affects, this is your like PD function of the PID strategy for adjusting the duty that's applied. So to look at that a bit more, let's scroll down and look at the final duty and our base duty. So let's look at final duty, base duty, and then I'm just going to bring up the integral as well, which I'm going to zero out just for the minute to make it a bit more obvious what is actually going on. If we just zero that out and just bring the manifold pressure down so that integral gets completely back to 0. Okay, so let's do this again. So basically, as you can see now, target and the manifold pressure, you can see the error that's created. And in our base duty table, we've got obviously 45% at the moment. As you can see, this is being shown here, and we'll show that in a minute. And then the final duty is at 64. Now, this is due to the fact that you've got a 20% adder being applied here in the closed loop PD error table. Now, the axis that's falling this way is your manifold pressure derivative, so the rate and acceleration rate of the climbing of the manifold pressure. And what I can do to actually show that, if we just open up a gauge for map1 dt as a trace, 25 hertz. If I now adjust the manifold pressure and bring so it comes up, so if I bring it up very slowly, you can see the map1 dt hardly changes. But if you've got a turbo that comes on extremely quick onto boost, you can see there the map1 would be a larger value. So as it climbs, so let's bring it down. As it climbs, the value would be larger. So it'd be coming down to here, and you can see that's why the values drop here, so that you're not actually having so much of an adjustment being applied to overshoot then the target. So the general shape of this actual wastegate control duty table should make sense then in why it's populated that way with the derivative function. Now, if you are having unstable boost control, then obviously this is the table you would first look at adjusting. But at this given point, these values should be a good starting point. As we scroll down the list, we've then got the post-restricted pressure control, PRP, and the turbo speed control. As I said earlier, we're not really going to go into that too much because it's just a basic generic wastegate control. But we are going to look at the integrator. So the integrator is the I term of the PID function, and currently, as earlier, we zeroed that out. Now, what this is basically brought up based on is basically the first thing you've got is the integrator enable error threshold. Now, this is based on the value which is called WG3 map error percentage 1. Now, what this is this is actually looking, I'll just make this larger. This is looking at the values that are actually present in your error demand table. Okay, so if I basically, what it's actually doing, the integrator is based on what your PD is actually working from. Okay, so if I just set this all over to say -20, you can see your WG3 map error percentage is actually at -20. So what you can do is in the integrator control, you can actually set a enable error threshold of when you want the integrator to be active. Okay, so if you don't want the integrator to be active at very large error thresholds, then you can make that lower. And we're going to just do that now. So let's just make this at say -10. Put in there -10. And then what that means is if I even go into the integrator gain in here and just populate some sensible values in here. Let's just put in here 0.1 and then here -0.1. Okay, now what you can actually see, because the error is very small on this now, the integrator is actually present. But if I bring my manifold pressure down, okay, you can actually see where the error percentage is obviously at -20, the integral is not being applied. And if I slowly then bring that back up, okay, closer to the target of what we need to be, you can then see that the integral kicks in and works. Now this integral is a gain purpose, okay? So as you can see there, the integral wound up pretty quick with that. If you want to make it faster, obviously you can make it higher or faster. And if you want to make it slower, then you can do so by doing so. So just to show the difference in the effect of that now. So you can see the rate in which the integral climbs is quite fast. If you obviously multiply this by say 0.1, make it really slow, you can see then as I come into it, the integrator slowly winds up. Okay, the integrator is a great tool for like a slow adjustment in the low error points, really. So that if you're not exactly on target, basically what will happen, the integral will slowly ramp in the duty more to actually till you achieve that target threshold point. The values I've chucked in here probably like a good starting point. I wouldn't recommend to have the integral active in large error points, so at like a high at 25 and -25. And obviously these are just values I've just chucked in here. Generally this would probably look at something more like this. And then actually interpolate that down, like that. Okay. Now, the other things you've got in here is you've got an enable manifold pressure map DT threshold. So again, that is based on the map1 DT value that we talked about earlier. I generally am not really interested in that aspect of it, but you might find if you've got a turbocharger that is ridiculously fast in the way that it comes online, this might be a useful function. The breakpoints, there are breakpoints for adjusting the gain values, which are pretty sensible. And then you've got integrator gain reduction, map error threshold, and gain multiplier below threshold. Generally, these can just stay at default values, and they're pretty useful. Integrator minimum and maximum, this basically allows you to set your integrator limits, and the integrator decay filter function is basically so when it's the integrator is not being used and it's decaying from it, it just sets the percentage in which the decay is applied. Okay, then coming down a bit further, we've got the gear cut control. If you've got a sequential gearbox, what this does is it allows you to, first of all, set a duration of the gear cut adjustment, so how long this adjustment will be present for after the gear cut request has been present. And then you can choose then the integral action, so you can choose to reset it or freeze the item and leave it. Generally, the reset is useful because obviously on a gear shift, when you've got a gear cut present with maybe lots of ignition retard or ignition cuts, you do get a lot more turbine energy, and at which point you want to make sure that all the item is reset so it doesn't slowly overshoot at all. Okay, then the overboost torque smoothing. This is just a way that you can actually smooth the torque of the engine with ignition timing based on the wastegate error and the target. It's not something I personally use in most cars, but if you've got something that is very keen to ensure the torque control is maintaining that point and the boost is over the target ever so slightly on error, let's say for example, you're wanting to maintain, say, 200 newton meters exactly, and you weren't using the torque control. If you know that given boost that it can maintain that, what you can do is you can pull out timing if you're over the target slightly or under it, and you add timing if you wanted to. But it's something that was used for a one of a kind race application. It's not generally something that's used in most of our plug-in kits. The wastegate control duty. So what you can do here is you can change the x-axis to be either based off engine speed or manifold pressure, and then you can set the breakpoints here. Currently, it's just set as it is on the S6, so you have your manifold pressure target on the one axis, and then the RPM on the other. This is probably the most useful way of doing it, so that if you find that, say, you've got a lot of exhaust back pressure and you need to ramp in more duty at higher RPM, then you can do so in this table and stop the PID aspects having to work so hard. Now, obviously, you can see at the moment our wastegate map1 target value here is at 2000. So the control strategy is using these base duty values, which I'm highlighting here. If I come into the manifold pressure target and set this to 1500, you can see that the base duty is adjusted to suit. You've got simple adjustment duties here for pedal position and barometric pressure. And you then also got the wastegate control duty learning. So if you come down and actually then go a bit further down, this is something that we haven't done a help video on yet, but we'll cover that later. I don't want to overcomplicate it for people at the moment. The output linearization allows you to set a different output linearization for the given output. On this particular instance, the wastegate control is controlling the lower part of the wastegate, and the solenoid is plumbed up in an inverse way. So hence we've got the PWM output duty linearization flipped. If you want to change it the other way, it's a simple math flip an X, and then that way your duty cycle is relevant to the output that the ECU output gives. The antiphase, as explained earlier, is for allowing you to have the opposite of what your wastegate duty final would be. So if you wanted to have a top hat and lower hat control, you can have the two solenoids and then invert the axis if you wanted to. Now, just touching base on something that was mentioned earlier in the video about the custom maps that are applicable to the standard strategy. What you can actually see is on the stage target area, I had these two custom maps, and you can set custom maps based on your target limit or your maximum pressure. In this particular application, it was done based on the stage target limit. So as you can see here, I've got two. One is based on a user-defined input, so you can have a separate switch if you wanted to for adjusting it. And the other one here is based at like a high load timer. This one's quite useful to use in applications so that if the client is on load for an extremely long amount of time, you can actually start to drop the boost down so that you don't start to overheat things. This is really simple to do. You can just open a gauge for a high load timer. Let's just open that now. And then the variables to adjust that are under logging functions, high load burst logging. So you can set the pedal position, the manifold pressure, and engine speed for that bit to become active. The pedal position is true at the moment, the manifold pressure is true, the engine speed is not, that's a bit too low at the moment. So what I'm going to do is I'm going to bring the engine speed up, and then you can actually watch that timer kick in, as you can see here. And actually then what you can then start to see is as the timer ramps up, I'm just going to adjust this here, you can then adjust your target, and if you watch the target limit adjust, you can see there it's coming down to suit. It's a nice little function, allows you to keep an eye on the engine temps, etc. You can obviously set up custom boost maps for based on your exhaust gas temperature, your EGTs, your water temperature, etc. Anyway, if you wanted to do it that way, and I'm just going to go over how you do that. So if you go to View at the top and then Customize and Options, and then go to Configurable Purpose Maps. I've discussed this. There is another help video on this, but I'm just going to go over it again. So what we're actually going to do is we're just going to create a new, let's go for a 3D based one. So this one's not in use. So you're going to click on that and then press enter. Can't do it when we're online, so say disconnect. And then, as I said, we've got wastegate adjustments for the final duty and the wastegate map max. And then there's obviously other ones here that are wastegate target adder. So let's go based on the wastegate map max adder. So let's create one for there. Just click proceed and tag. And then we're going to set the variables that's going to be set on. So let's say we're going to have one based on engine torque limb, which is like a reduction request from the DCT gearboxes to reduce the torque. So obviously heavy amounts of retarder be used there. And then we can have one based on water temp as well. Once you set those breakpoint, the variables for the breakpoints, press View and Customize options again to go back. And then we're going to go to that new custom map that we've created and enter some breakpoints for it. So that'll do for this, just for example. And then the water temp ones will do as well. So what we can actually now do then is we can actually adjust the manifold pressure max value based on these two parameters. Now, if we go up here, you can actually see that they're actually now populated. This calibration has actually been added into the wastegate control as well. And then you can have an adjustment on these values to adjust how you want it on the car as well. Remember, it is offline, so you will need to save this. Just put here wastegate test and then reload it back in. So file close, device connect, and then go file load, and then load the wastegate test. That then loads that custom map, saves it into the ECU, and that's fully programmed in there then now. And you can see that that's present and active all the time. Hopefully that's been helpful.